Stars so bright in the sky. On Arizona nights they fly. Nebulae in colors rare. Galaxies beyond compare. Sky tour in the night so clear. Brings the universe near. Real-time wonders to see. Streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds. Stories of the cosmos told. Through the lens, a distant dream. Living real like a gleam. Far away, up so high. Across the stars beyond the skull. Through the lens, a distant dream. Living real like a gleam. Lift your eye up so high. Across the stars beyond the sky. Sky tour shows us the way. Every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new.
Hey everybody, welcome to SkyTour live stream. It is I, Mark, here with Daryl Mason. Hey Daryl, how are you?
Hello, Mark. I'm well. You? Hello, everybody.
I am doing just fine. I am going to restart the telescope here. We're going to just restart. So we're going to do it now. Usually I have this done when you guys come in. So let's see. Make sure everything comes up like it should. You get to see a little behind the scenes here. There's our alrighty, bring this over. How is everybody? How you guys doing out there? Things going well? Alright, I'm gonna bring us up and connect. Alright, and then we will come out of here, do our GPS. Okay, And we're good there. All right. And now I will connect our camera. You'll see the stars in the view here in just a second. Here we are. We have our stars. Now I'm going to do a plate solve, figure out what's in the field. Resolve failed due to failed to find solution. Okay, I know why. We gotta give it a little more. Let's move us to the east a little bit. And down a little. There we go. There we are. Okay, so we have some stars here now. These should allow us to solve in this region. Let's give that a try. Why is it saying that? Not sure. Oh, I might know why. Where are we? 21. Okay. Let's see what it thinks we're doing. Alright. Just working through a little issue. Oh, there goes a Starlink satellite. That's pretty. Alright. It gets in the way though, doesn't it? There we go, over there, huh? Let's go here. Oh, wait. We'll go to max here. I'm trying to get the system to find the stars we're looking at, and it's not giving us the star solution, and I'm gonna see if we can figure it out here. Alright, we're gonna try this now. It's gonna run through everything. Yeah, okay, so it figured it out. So let me try this now again. It knows where it is. Maybe this will help now. Okay. This annotation works only if the telescope has a rough idea where it is. Because it didn't know anything about where it was, which happens from time to time, it didn't know. So what I'll do is I will bring this right ascension up. It says we're at 1941. I'm going to put these coordinates here manually. 1941 and 32. And then we go to the next one. And we are at 02 21 27. And we'll synchronize, and it should go there. And it did. Okay. So now if we do this, it should not fail, because it was thinking it was in a whole different place. Yeah, see, now it knows. But there's no deep sky objects here. All right, so good. So we're all set. All right, so we'll go back to our system here, and it shows us that we're up in Aquila, the eagle. And while we're here, let's start up here with something that we often look at. We're going to try and hang out in the northern Milky Way tonight. This guy right here is what we're going to look at. This is a cool nebula up here that I don't know you guys have seen before. Maybe you have. But it's actually called the Tulip Nebula. And it's just beautiful. And we're going to head there now. Now we're going to go to the star that we're looking at right here. Oh, I forgot to change a setting. I have to change that. There's a setting I gotta change, so you'll have to bear with me on this for a minute. Whoop. Okay. It's trying to do a movement, and it's trying to do a high precision movement to the star. But I have to let it find it incorrectly before I can get it out of that mode. That's the problem I had when it started up. It did some kind of weird thing on us. Okay. Let's see if we can get this to do this now. Alright. So, I have to go here. And I got to adjust some parameters now. I'm going to set our right ascension guide setting to 15%. And set our declination to 22, which are the settings that I found work best. And then we're going to turn off something called high precision, because as it turns out, the telescope doesn't need high precision because we are able to exactly identify where we are, so we don't need it at all. Alright, so high precision is off, confirming. Yeah, okay. And now we'll come back and we'll see that we're probably already guiding. And we are. Okay, so now let's go see where we are. We're going to be looking up kind of near Cygnus here. And let's go back to this. So we're going to tell it to go there now. And the telescope's going to move a little bit. There it goes. And we should have the tulip in our field of view, and I believe that is it right there. So I'm going to bring it down. Could be wrong about that. I'm just gonna trust that it might know. Actually, let me do this. I can just do this. Let's do this. And plate solver for this right nearby. Okay, that's an open cluster. Alright, so I'll tell you what. I'm going to take that open cluster and I'm going to center it in the view. And from there I can jump over to the tulip, which is nearby. Unless that open cluster is actually right in the middle of this. It might be. I'm going to get around to saying hi to all you guys in a moment. I just wanted to work through this little issue we're having here tonight. It's a nice thing of having the ability to fix things from a long distance. And you got to kind of see it, so that was kind of cool, actually. All right, let's do this. There we go. All right. Now we're going to come back to our location. See, that's where we are. All right. And we're going to tell it to come here. Go there. And we should move over a little bit. Okay. And then we should see. It might be here. I'm going to have to just try it. It was already here, so maybe it's here and I just don't see it. Let's do a 20-second shot and see what we got. We'll live stack just in case we have it. And we'll get out of low light mode and go into deep sky mode. see what we got. Did that one work or not? Yeah, it did. Yeah, okay, so we did get it. I just have to set colors up, do our color correction, and do this. Yeah, so there's this nebula. There's the tulip right there. This is a beautiful band of nebula associated with it. So I just didn't recognize that we were at that location. Nice. Very, very good. Okay, so here's our black level. We're going to move that black level over near the center, and that will blacken up space behind the nebula without getting rid of the data for the nebula. And as you can see, it really shows the nebula well. Okay, so this is sort of in the heart of Cygnus, in the heart of the Milky Way up there, and it really is a beautiful location. You know, you can't come into this area. You can't come into this area and be disappointed, because there's always something to look at here, you know, and it's just beautiful. So while we're doing that, I am going to set up one last thing. I'm going to bring up the chat so I can check you guys, talk to you guys.
Tiffany's here.
Tiffany Echo. Hey, Tiffany. Tiffany, I left Mike a message like days and days ago, and he never responded. I'm just wondering if he's doing okay, or if he's just been crazy busy. All right. So going up to the top, let's see. Tim F was the first one. That's cool. Weather is Crazy is with us. Very cool. Hey, that's a new one. I haven't seen you before. And Goblin's with us. Goblin's a previous winner of a giveaway, courtesy of Tiffany and Mike, who is Calibos. And let's see. Weather is Crazy. This music is part of the YouTube gallery. The music at the beginning is one that I wrote and composed, and I used AI to do it. I told it what instruments to use. I wanted to get a certain look and feel, and so it composed the music, but I told it what instruments to use and everything, and wrote all the lyrics. So that first song is that one. And then, Daryl said that. Donald Kunzer is here. How you doing, Donald? And Roxy NYC. Hey, Roxy. Yeah, Roxy just got back from a trip, man. She was down in Bourbon Street, man. Hey, Wayne Pinkham, how you doing? Wayne is a cool guy. He actually, when he went to Hawaii, I tell the story. He went to Hawaii, and he actually went to Mauna Kea, lucky guy. And he actually brought me back this really cool t-shirt, which shows all the sizes of the mirrors on the mountain for all the different telescopes. It's really one of my favorite t-shirts. So you gotta love it. So that was very, very thoughtful. So I always call him out and say hi when he comes in for that reason. He's just a very thoughtful person. Hi, Wayne. Judy M is with us. How you doing? Stuffy, what's going on? Stuffy's in North Carolina, and I'm glad you have power and everything's going okay down there. And then let's see, you got Fantasies with us. How you doing, man? He's a great guy. And Dew W, hey man, Dew is with us. Just go over COVID, boy. Hey, look, I'm gonna tell you right now, I had it 6 times, and it became a cold and just got me mad. So let's hope that that's the way it stays. We have 211 Milkman. Hey, how you doing? Nice to see you. Waldo Hiding's with us. Yeah, that's cool. Stan at Two Rivers Observatory is with us. How you doing, Stan? Hey, Stan, I wanted to let you know and tell everybody while you're here. And I'm going to share with you that this telescope out in the middle of the Arizona desert is probably getting moved at some point in the near future. Maybe relatively distant future, not sure. But we actually have a location for it that's darker, and that would allow us to set up both telescopes in the same building. So we'll have them in the same place under the same conditions. One will be a high focal length, meaning high magnification system, which you have not seen yet, and one will be this system here again. And this system will be change to an equatorial mount from the fork mount that you see. The fork mount, you can actually see we have a on this side, and on this side we have a fork. Sorry about that. I should have just let that come out. Okay. You see on this side, that'll go away in a second. The fork mount here and then here, and the telescope barrel goes up in between. We're going to convert that to an equatorial mount and put it on a higher pier so we can see over the top of the building as best as possible. All right, so and that's going to be at a new location. Now we're going to work this so that the telescope will not be down for more than a day or two, if we can manage that. Right now it looks very promising, and where we're moving it to is going to be a place where there's other professional telescopes on the site. So we're going to be moving it to a place where people have already figured out that this is a great site to move it to. It's another location in Arizona. But that's to come. That isn't here yet. This is pretty, Daryl.
Yeah.
Yeah. At first I was thinking, I'll center this up, but I wanted to capture this cloud. It's really pretty. This is kind of a nice composition. Really liking that. Susie Karasik's with us. Hiya, Susie. Susie is a previous winner of equipment from us. Yeah, she was in Glastonbury in the UK, you know. So she's jet lagged from just getting back. But I think the jet lag works on your behalf. Because, you know, you're kind of in like, well, maybe not. It's kind of late for you in Glastonbury in the UK right now. But you're handling it, Susie. I'm proud of you. Thanks for dropping by, too. Hey, Sam S. Sam S is with us. Yeah.
Susie, were you at the Glastonbury music thing?
No, I don't think so. I think she went in support of a conference presenter. I forgot Susie. She'll tell you. Hi, Wayne. That's cool. This is beautiful.
I'm gonna quibble for a second here.
Okay.
Fork mount is an equatorial mount.
Yeah, but I'm going to a German equatorial.
Well,
I didn't say the full thing yet. Yeah.
Portal to Ascension Conference, she says.
Yeah, that's what it was. I couldn't remember.
Sounds pretty heavy.
It was heavy. All right, so let's see. Did it know what this was? I don't remember. It knows the stars, but it doesn't know this guy. But we can figure this out, because we just have to go here and bring up our data and go to DSO, which stands for Deep Sky Object, and select additional catalogs like the Barnard catalog of dark objects, the Sharpless catalog, and then the Lens Bright Nebula and Lens Dark Nebula. And that should do it. I bet you it'll be in there. Let's see. Oh, it's part of the Cygnus Dark Cloud. Yeah. It's not one of those. It's not a Sharpless object. Vandenberg, maybe? I'll do Caldwell, too. Why not? Okay, let me come out. And, okay, so it's, by definition, the Cygnus Dark Cloud Tulip Nebula. There you go. And that's LBN 168. So Lens Bright Nebula, it's also Sharpless 2 101. So it's got multiple designations. And that's this guy right here. Look at that. And this is a real pretty picture. We got 25 of these done with no errors, no rejected. I like it. All right. Let's zoom in, shall we? Okay. I see an interesting piece right here. This looks like almost like a bow shock, which is a shock wave created by stellar winds. You know. Yeah, Waldo, what's a hen weigh? About 3 pounds. Yeah, this is cool. Okay, looks like I have a little bit of a focus issue here. Yes, I do. I can actually sharpen this focus, so I'll save this anyway. I'll call this a Tulip Nebula. Always save, just in case. Just in case. All right. I keep forgetting to change my lighting. I want the lighting to be proper for the system here. Okay. So let me do that. I'm gonna go here. Go over here. You can't see this, but I'm picking STLS. All right, there we go. All right. All right, so this guy is gonna be saved here. And then we'll do a refocus and come back and do it again. You'll be surprised at how much better this looks. Okay. So we'll come back here, go to our low light mode. Again, we'll leave it like this because it doesn't matter. Alright. There we are. Alright, and now we'll do this guy. I'll move it out one step so we have an obvious bottom to that curve. All right, one more step. There we go, and then we go. The nice thing about this system is we can auto focus all the time here. We can and as soon as the telescope is looking for the images, you'll see it. You'll see that it picks images. Okay, and as it picks the images, it tries to minimize the size of that image effectively, and that filter that it uses is a full width half maximum filter. It's a filter that takes the size. It's like a bell curve, like a curve that looks like a bump in the middle. That's the star image. So they want to narrow that image and make that bell curve as narrow as possible. And when it finds the narrowest spot, that becomes the bottom of the curve. In other words, the smallest value down here. So you see it's coming down, coming down, coming down. Then you'll start to see it going up and up and up as it goes back out of focus. And that'll make a curve. And then whatever's at the very bottom here may not be one of the points it actually moved to, but it'll interpret where it went and mathematically solve for that location. See, it's going back up now. So we're going to end up seeing a line show up right about here. I'll do a predictive arrow. Okay, now it looks like it's going to be about here. There it is, right on the money. Okay, so now that's our best focus. So right now we've got 9 through 12 up here. You see 9 through 12 of the samples, and then it'll be 10 through 12. And if it finds the best one, it may stop early. Okay, and that's exactly what it did. It stopped early, and now it's going to go and move the telescope to that focal spot, and you'll see the stars become very, very sharp points. Now you saw what we had before, and now I'll show you what we have now. So the problem is, when the telescope tips up, the mirror moves an imperceptible amount, a fraction of a millimeter, and that's enough to cause it to be slightly out of focus. And so, and that's called mirror flop. It's something that happens in telescopes. It's not uncommon. So right now we can go back to our 20-second exposure, which is 20,000. As you see right there, 20,000. This is the exposure up here, milliseconds. And 20,000 milliseconds is 20 seconds. So we're going to go into our deep sky mode again. Jump into our live stack. You'll see the previous image. It looks a little fuzzy. See that? This next image will be very different. All right. And we're going to clear this to make way for it. But I want you to see how fuzzy this looks. And then once this is cleared, watch how much sharper, even though there'll be some noise while we build up the image. Watch how much sharper the image becomes. Look at that. Now we're sharp. I'm going to immediately change it, make it better by doing this. Remove color noise. Bam. So now we have sharp stars. We don't have all those weird little shadows and refraction issues. So now we can actually get a beautiful, sharply focused nebula photo here. So we'll get it back in just a minute, as you can see. Also, it's a little too blue. We want to color correct. Okay, look at that. Now it's more red like it should be. The red, as we've talked about, is from ionized hydrogen. Hydrogen, very simple atom. It's a proton with an electron. If you add ultraviolet energy into the equation, you add ultraviolet energy into the hydrogen atom, the electron will absorb that energy and can go higher and higher in its orbit around the atom's core, the nucleus. And if you give enough, it will literally leave the atom for a period of time and maybe rejoin. If it rejoins, that's called recombination. That electron will bounce down to several quantum levels, which is where the term quantum mechanics come from. And they're actually numerical levels, 2, 3, 4. And when the electron jumps to the predominant one that always occurs, which is level 2, n equals 2 is called, you get a red light that it gives off because it absorbs energy, takes in light, all right, ultraviolet energy to leave, but when it bounces back into the atom, it gives off light. And when it goes into that lower level, n equals 2, it gives off an orange glow. So this is the hydrogen glow from recombining electrons going back into the hydrogen atom. Or ionized hydrogen glows red. Simple as that. You can think of it that way too. Waldo says, best YouTube channel in the universe. Well, thank you, man. That's very, very kind. Yeah, it'll be saved. You can watch it later. You can be sure that it'll be up there. Hi, Cindy Murphy. Yeah. Yeah, the new observatories. Susie says, great news about the new observatories. Yeah, I mean, it's going to cost us a lot of money to place both telescopes there, but I'm hoping we can start a fundraising campaign to actually, get a little nest egg. I'm not making any money in this. There's no money going to me on this. No money going to Daryl. We're doing this out of our passion, And you see Izabela. Isabella's not making any money with this, and she's one of our greatest helpers. Tiffany and Mike, they're spending money to get equipment for you guys to get raffled off here in SkyTour. And Tiffany, we'll be talking to Tiffany and Mike again and see about equipment giveaways, see if they want to still continue that. They said they do, but we'll see. Yeah, very cool. Yeah, this is much better. See this? Let's zoom in. This is 10 shots. Oh yeah, look at that. So much nicer, guys. So much nicer. Stars are like they should be. Let's go to enhancement. I'm going to make it a little more noisy by doing this. But that brings out some of the detail in there, see? And the stars are even more sharpened. Look at that. Really nice. Oh, Susie, I'm glad you liked the science part of this. Waldo. Yeah. You've helped me fall asleep many nights. Well, he means that in a good way, I hope, Daryl. Kathy Prunasek's with us. That's X-Lady. How are you, sweetie? So good to see you. Very nice. This is what the universe has to offer us. It's always got something beautiful to see. Tiffany says, oh yeah, we're continuing the giveaways. We're just on hiatus at the moment due to life. LOL, but we'll do them again soon. I thought so, Tiffany. No one's pushing you. You've been so damn generous in the last year that, my gosh, it's wonderful. All right, we've got 15 shots here. I'm going to raise the music for a bit, and I'm going to go and grab a bottle of water. If you guys will give me about 35 seconds. Daryl, I'll be right back.
Okay.
You can talk if you'd rather.
I will.
I'll be right back. You guys let me
Sam
know if it
asks,
talks bad about me.
do recombining electrons always return to an energy level closer to the nucleus? Yes, they do. They move toward a minimum energy state, I guess you would say. And that quanta of energy it accumulated from the ultraviolet is re-emitted as a red photon of light. Distinctive color of hydrogen alpha. Anybody watching the Major League Baseball playoffs? Yankees beat the Royals, and the Dodgers just went ahead of the Padres again.
All right.
I think Shohei Ohtani, the Japanese Dodgers player, that guy's really something. I predict Hall of Fame for him in the future.
Let me answer Sam S.'s question. Do recombining electrons always return to the energy level closest to the nucleus of the atom? No. In fact, the hydrogen atom has multiple quantum levels. So some of the electrons go to a different location, different level when they come back. When an electron gets ionized, it'll come back at a different location. But the one that's predominant, the one that dominates, is hydrogen alpha. Okay, and that's the one that takes it down to the n equals 2 level. All right, there's several others. There's hydrogen beta, okay, and others, and hydrogen delta, and so forth. And those lines, those emission lines, are in different locations in the spectrum. All right, so the hydrogen atom can generate a full range of this stuff and responses like that. However, when they do go into the atom like that, they mostly go to the n equals 2. So you're seeing, there's undoubtedly other types of hydrogen transitions, that we call those transitions, going on in here. But this one is the dominant one, and it's a red color. I will say this. When we do, with the new system, we're going to have a spectral capability to look at the spectrum of the stars. We have a program we're going to use called RSpec, written by Tom Field, a good buddy, and it's going to allow us to see the emission. Now, if we see a supernova in a galaxy, we'll be able to take the spectrum of the supernova and see emission lines in the spectrum, and be able to, make sure that you can see what's happening in there and see the emission lines in a supernova. So that's all cool stuff.
I'm just not good at talking anymore.
Why?
Well, because you step on everything I say. I answered Sam while you were gone.
Oh, I didn't know that. How would I know that? You've answered people when I've said things too, and I've never complained about it. I mean, it's information people get. It's good. I was gone, so how would I know? So that's a beautiful nebula. Sam S. says he's reading a book about spectroscopy that talks about this also. Good. Very good. All right, so we're at 28. We'll go to 30 on this, and then we'll save it, and then move on to the next object.
Can you zoom back in for a second?
On Stellarium?
Yes.
Okay.
Fish on the what? Fish on the Platter Nebula?
What? Where?
Right below the tulip.
Oh, look at this. Fish on a platter. That looks like a dark nebula. That's this guy, right? One of Lynn's dark nebulas? Oh, Barnard 144. Oh, that's interesting.
Might be worth looking at.
Yeah, because let's get our field of view and see whether it's already in our field of view. Technically, we are looking at it. That must be this.
Huh.
Yeah, because we got the tulip over to the right. And this is the fish on the Platter Nebula, too. How about that? I never saw that, Daryl. All right, we got 32. Let's... Wow. I don't see a fish on a platter. Let's do an over processing. We use this just to kind of show what's hiding in the background there. I'm assuming this is what they're talking about, right?
I assume.
Yeah. Interesting. Huh. I'll drop that back down. Actually, let me see if we can get any information by doing this. We can actually take a negative of this image. In astronomy, we do this often to examine things that can be seen in a negative impression rather than a positive. Sometimes. It doesn't always work that way. And this isn't helping in this case. Alright, so we'll get out of that, Daryl, and move on. That's really pretty, though. So we'll save it. We've had 36 shots without any kind of errors. That's good. Susie Krasik says, I really love this part because when I can squint my eyes and see all kinds of things. Yeah, you can. Thanks for putting up that address, Daryl.
Yep.
Okay. Well, now that we saved it, you will get an image on the server, which is here, skytourlive.org, as you see on the screen here. If you scroll down, it will tell you how to acquire these, how to get these from our server. And what you'll get on the server for this one, for example, if I save it one more time, we'll save it one more time and save exactly as seen with 38 images, you'll see there's a PNG file. The file you get is this one right here. It's going to come up. This file is up there, and you can download this, check it out, look at it, and it's really something. You can enjoy it, use it as a desktop background if you like. You can zoom in on it, do your own kind of hunting for things, because this is exactly what people do with our data sometimes. And that will be a lot of fun for you to do if you want. And it's also very, very exciting to take part in something where you might actually discover something. Okay, so we'll come out of here. Go back into low light. Alicia, how are you? Alicia's here. Alicia is going to be in Arizona. She's going to go over at Marianne's house. And she's going to go with Darlene and I think Donovan, her husband. And they're going to hang out and check it out. Very different from Texas.
I sense a hot tub party in their future.
If she had a hot tub, maybe. But she does have this most incredible built-in pool.
I thought she had a hot tub too.
No, she doesn't have a hot tub. She just has a beautiful pool, but has a waterfall that you can actually sit under. It's the coolest thing. Yeah. Oh, she's going to Tucson at the end of this month. Very good, Alicia. Is that for school? Okay, so we got that. Let's go back to here. You know, in the early days with this particular telescope, Daryl and I would just like scroll around the sky and take pictures and say, wow, that's cool. Whoa, that's cool. Look at that. That's neat. Remember that? We didn't even know what we were looking at sometimes because the telescope didn't know where it was. And we had to work that out, have it figure out how where it was looking. And when we did, it became an incredible way to navigate the sky. You know, but for instance, like this is the Crescent Nebula, and this is something we wanted to see, and we would never have been able to find it unless we just sort of like randomly went up the Milky Way and kind of made a guess as to where we were looking. You know, but so now we can actually more precisely locate things, and in this case, we're going to move to something called the Crescent Nebula, as I mentioned, and you'll see a fuzzy thing show up in the view here. It's right here. It's kind of faint, but it stands up to checking it out because it's really cool when you see what's really going on inside here, when you learn about what's going on inside here. So we're going to center it up. Okay. Right there. Bring it down. Okay. And that's good right there. All right, and we'll just move a little bit westward. Okay. This one doesn't need a whole lot of time, but we're going to do 25 seconds because I noticed there is some very faint material mixed in that I think we want to see. So we'll go into our low light mode and our deep sky mode, actually. Go into deep sky mode. And you'll see the Tulip Nebula that we just took. Beautiful nebula. And that's in the buffer. That's not going to be lost when I do this, when I click clear. Hello, Catherine Messick. How are you? There it is. Look at that. So that's 25-second shot. Let's zoom in. It's a little early. We only have one. But I want to show you something cool. I'm going to take off the additional enhancement here. We don't need it. It makes it look noisier. Okay. But you see, there is a halo here on this side, plus a little more stuff out here, plus some stuff in here. that we haven't seen before. Now, you remember, Daryl, with the other camera? We saw something in here, and it was like, it looked white.
I don't know, man, no.
Okay. But it was like a whitish haze in here. This is more blue. So it's actually a little bit more color correct, I think. Although maybe a little too much blue. Look at the detail in here, guys. There's so much detail in here. This is called the Crescent Nebula. It's the result of an extremely hot star that has expelled its outer layers. We've heard about that before with planetary nebulae like the Dumbbell Nebula and the Ring Nebula and others that we've seen. But this is a very, very different process, because in the stars like that, like the Dumbbell, that remaining stellar core in the middle is a white dwarf. This, however, is not. This star has expelled its outer layers and is still furiously fusing in here, and it's still a true star. It's still doing fusion, and its outer layers are being ionized by the extreme stellar wind and heat and the ultraviolet energy that's ionizing it. So the temperatures in these are like 45,000 Kelvin. If you look up the Kelvin temperature unit, you'll find that is pretty close to Celsius, but you know, we're talking, it's 273 off of Celsius, but this is just a very, very hot region. Nothing could survive here. And you know, you've heard Daryl say in the past that if something got close to a Wolf-Rayet star, which is what these are called, it would probably melt you. And I would say that he's probably correct about that for sure. That's beautiful, though. Now, the thing about the Wolf-Rayet star, which is right here, is that this Wolf-Rayet star is destined to go supernova at some point and obliterate itself. It's already done what looks like a planetary nebula. However, it's going to send off its entire guts in a supernova explosion, and return everything that it's manufactured in its core for elements to the cosmic medium.
I dare say it's much larger than a typical planetary nebula.
Yeah, you're probably right about that too. Right? Because they're like, typical planetary nebulae are like 2 light years across at most. And as Daryl was saying, those strong stellar winds we've been talking about probably are pushing this material out further. What's the distance of the crescent? Do we have it? Maybe it's in here. Let's see.
5,000 light years according to Cosmic Ray.
Okay, it says 4,700 here. 4,700.5. That's funny. Okay, so if we figure 5,000 light years, the Dumbbell Nebula is about, say about this big in the screen. And how far away is the Dumbbell? About 1,500? 1,200?
1,500, something like that.
Yeah. And at 1,200, say, light years away, as Daryl just said, this would be about the size of the nebula. And I can actually show you that a little better. Okay, so this might be like on our screen, that's about the size of the Dumbbell as we see it at 1,200 light years. All right. Now, if this thing here, right, was 1,200 light years from the Earth, it would cover a massive size in this field, and not the smaller field size. So when Daryl says that this object is a lot bigger than a planetary, it's a matter of scale. Dumbbell's closer, but smaller than this thing here. This is bigger than a Dumbbell, and it's 3 times as far, 4 times as far almost, right? So clearly this object is powered by forces much more powerful than the planetary nebula like the Dumbbell or the Ring Nebula or the Helix Nebula. The Helix is actually really close to us. And it's about this size, and that's what, 600 light years?
I forget offhand.
Yeah. But it's the closest planetary nebula to us, the Helix is. We've photographed it. And it's just about a little smaller than this. Maybe about that, quite about that size. We are zoomed in, to be fair. So let me zoom out, make sure we got that right, because... Yeah, okay, it's about the same size. And it's about 600 or so light years away. And this is 5,000, and it's as big as the Helix. So if this was closer to us from 5,000 light years away, it would fill this screen. So the forces powering it, like I said, are absolutely immense and covers more light years. It's kind of a good night.
Ray says the crescent's 25 light years across.
Okay.
So 12 times the size of a planetary.
Mm. Yeah. Yeah. Or 10 times. 10, 11, 12 times.
Well,
25 light years across. 2 light years. How many dumbbells we fit across that? You know, that's
about 12 and a half.
yeah. So that's pretty good. I'm seeing detail here we haven't seen before, and I'm not even using the enhancement here. If I put on the enhancement, does that help us or hurt us? Wow, look at that. We're seeing some really cool detail in here. Look at that. A little hook of material. That may be dark nebula in there too, as opposed to a gap, but because this is all dark nebula back here. So I'm gonna guess this is a gap here, and you're seeing through to dark nebula behind it, because we know this is dark nebula here. Wow, that's really pretty. Let's do color correction, see if we can draw out some of the additional red colors nearby. Yeah, this should do it. Let's back out a little. Yeah, look at that, guys. Look at how much red nebula is here. This is the hydrogen gas glowing, as we've talked, as Daryl described.
There is a notably more reddish area to the left, lower left of the crescent.
This one here.
Yes, wonder if that's part of it.
I don't know. Because we see a darker red area here. And these are probably areas of higher hydrogen density, so that the red looks more pronounced. I think it has to do with the density in the interstellar medium there. But look at this star. Look at that beautiful star. That's a really pretty star. I wonder if that's a carbon star. Let's go back here. Let's go to the crescent. Let's look at the field. And let's find that red star. Alright. Let's make sure we're where we are here. Okay, we're pretty much centered there. So I'm going to synchronize on that.
Looks like those two stars at 3 o'clock in Stellarium.
Yeah. These guys?
Yes.
Yeah, those are the ones you're talking about. The lower one looks like it's supposed to be the redder one. And that's a carbon star. Very good. Okay. How do we know? Because it has an N designation. That's a spectral class. It says spectral type C-N5.5. C stands for carbon, and the N5.5 harkens back to the old classification scheme we had, where we had for stars such as this, we had OBAFGKM, but then we had RNS, and the RNS was deprecated, so to speak, and we were left with a new designation for the N types, which was the carbon stars. And so we have a carbon rating. So that looked like a carbon star, and it is. That's just gorgeous. I didn't know until tonight that there was a carbon star right near the crescent. That makes a beautiful pair, doesn't it? That looks really nice. Wow, and the detail, it's just coming in beautifully. We've talked about carbon stars before. They're red giant stars that are in the second coming of their red giant stage, a stage known as the asymptotic giant branch, where they've gone through helium burning, and now they're actually growing into this second red giant. They go to a red giant, then they start to fuse helium into carbon, and they shrink a little bit, get a little hotter, and so then they run out of the helium, and so the core contracts, which blows the outer layers up bigger, and so they become a red giant a second time. And that is the asymptotic giant branch, or the AGB we talked about. And it's during that time that there's dredging up of material inside the star. And if the star made a lot of carbon, you're going to get some of it up near the surface right here. And it shows on the surface as a reddened light, because the carbon is actually making molecules on the outside of this gigantic red giant. Because way out here, as opposed to in the core of the star, the temperature is only about 3,000 Kelvin or 3,500 Kelvin. So that's actually cool, quote unquote, enough to make molecules. And molecules of carbon will make like a soot in the atmosphere of the outer atmosphere of the star, making it look red. And you'd be forgiven for thinking that this red is this star's light reflecting on it. That's not what it is, but it's just kind of cool. We'll go to 32 on this, and then we'll move on. Really nice details in that. Okay. I'm going to change the name up here. I don't think Izabela knew we were going to stream before she went to bed.
I don't think so.
Alright. We'll save that. Susie Krasik says, incredible. Yeah, it is. It really is incredible. It's incredible to think that a star like this, this is a doom star. If you're anywhere in the region here and you have a planet that has any kind of planets around it, this star's eventual supernova could be the end of you. Not necessarily this nebula, but if you're like far enough away, but the ultraviolet radiation that's getting to you from this star could be enough to damage you. But if you survive, you might say, oh, well, we're good. Unless the star then blows all this material out when it blows up, and that material comes to your planet. We have no danger of that from any other star near us right now. Hey, Creeptasia. Creeptasia's with us. Wow, that's really something. Okay, last one. Save. Save exactly as seen. You have any suggestions for a place you want to go, Daryl? We're going to get out of this now.
No.
Okay. All right. Okay, my discretion. Let's go back here. Zoom out. Okay, this, and you've heard Daryl talk about this one before. This is just where they stopped taking pictures of it. It's not a big square red nebula. This is actually the Gamma Cygni Nebula. And the Gamma Cygni Nebula is really cool looking. But we won't look at that tonight. I think I want to look at something that's actually a little bit more interesting. And that's down here.
I suggest the helix.
Yeah, it's up, isn't it?
Should be, I believe.
Yeah. Well, we've looked at the helix, but I will look at it. I would like to check out the elephant's trunk. This is a really pretty nebula as well. So we'll do this first, and then we will do that. So we're going to see the telescope pointing way over the building as it heads toward the south, toward the north. There it goes. Going to look toward the northeast. And we'll see two stars come in that are stars that are part of this nebula. And I think that's these guys. Right there. They went away. They're going to come back. Let's bring this over. Alright, there they are. Okay, so we're going to keep coming. These weird marks, these are just graphic anomalies that occur because we are streaming using Starlink out there. Okay.
Whoop. Excuse me a second, please.
Okay.
I forgot to do something.
All right. That should be good. And we'll do a 25-second shot of this to show you what's going on in there. And we are guiding, as you can see up here. And we'll do a stack now on this. This is our deep sky mode coming up. And the previous shot of the crescent is right there. Remember, we zoom out, you get this beautiful red star. A gorgeous carbon star. That's really pretty. So this is up there for you to look at on the server. Again, skytourlive.org. And if you guys want to get anything that has these images on it, you can go up here and go to our Etsy store, SkyTour Live. Oh, yeah, there they are. SkyTour Shop on Etsy. SkyTour Shop on Etsy has nebulae like this on mugs, mouse pads, sneakers, you name it. Clocks. We have all kinds of stuff up there. And you can get, they're great Christmas gifts. Boy, oh boy. We have the Christmas Tree Nebula on a gigantic fleece comforter. It's just incredible. It looks beautiful. Cindy Murphy in the chat has one of those. And she loves it. Thank you, Catherine. I'm glad you like the music. Okay, so this is really pretty. Welcome back, Daryl.
Thank you.
We've talked about this too. When you look at nebulae like this, you see the dark nebulas. These are dust, as we've talked about. And then you see the dark nebulae that have hydrogen mixed in with them as well. And that you're going to see hydrogen with dust constantly throughout the universe. And when you look at a nebula like this, you're seeing hydrogen glowing, as we've talked about. And then sometimes you don't see a lot of it. That's because there's more dust in this region than hydrogen. And the hydrogen is not dense enough. It's probably there, but it's not dense enough to show through that particular region very well. That happens a lot. Okay, we've got 5. I want to show you one other thing too. This is the Elephant's Trunk Nebula. See, it looks like an elephant's trunk. And this is known as the Caravan right here. And it goes into this other dark nebula. But let's check this out. If we zoom in on the elephant's trunk itself, look what you see. Right in the middle, there's a round hole, an opening, and there's 2 stars in there. Well, this round opening is a cavity that's been carved by this bright star right here. It's young, it's hot, and it's actually pushing the very, very lightweight dust out of the center. And over time, millions of years, it's opened up a cavity in here. We see that a lot. We see that a lot with these. They open up cavities. Let's try to process this a little to bring that in. Let's change our dark level here. Bring it right to the edge. Look at that. Wow. That's really pretty. Look how this goes all the way out here. It's a big trail. That's gorgeous.
Susie, yes, hydrogen is about 75% of everything in the universe. Most of the rest is helium. And then everything else is in that last little bit.
Yep. Hydrogen's number 1. Helium's number 2. The third most abundant is oxygen. And the 4th is carbon, which you're made of. Alicia, gotta go to bed early, she says. Alright, well, you have a good night, Alicia. Thank you for dropping in for a bit. It was nice to see you here. You know, I've talked about this before. Carbon being the 4th most abundant and oxygen being the 3rd most abundant, it stands to reason. If carbon is very flexible, it's probably the dominant life supporting element in the universe, because the chemistry is the same throughout the universe. So I think carbon-based life, I'm a bigot, I guess. Carbon-based life is probably where it's at.
Did you watch that Kurzgesagt I sent the other day? Says there's more life underground than there is on the surface and in the oceans.
Yeah, it's microbial, but yeah. Yeah, that's really cool. You should tell folks about that because that pertains to the Europa Clipper mission and then the Europa lander.
Yeah. Um, there's a great video channel on YouTube called Kurzgesagt. Kurz GE. Trying to remember. Kurz GESAGT, I believe. They talk about all sorts of science stuff, and it's in cartoon form, so it's amusing too. Fun to watch. Their most recent vid I've seen said that there is more life on Earth underground than there is on the surface and in the oceans. And that implies a lot of things. They think they said there may be as many as 10 life-bearing worlds if that notion carries on to other planetary and lunar moon bodies in the solar system. All the usual suspects, and then maybe a few more. Europa, probably Ganymede, Callisto, Titan, Enceladus, etc.
Mars,
of course. That life may be indeed crawling all over the place out in the universe.
yeah.
And I said in comments in our chat the other day, again, I brought up the Horta. Not necessarily, silicon, but
Different.
things living underground.
Yeah, that's cool. Yeah, so if you guys want to look that up, look up more life underground than on the surface in Google, and you'll probably find that article. It's very well done. The other thing too is because we found life at our deep ocean vents, the hydrothermal vents, the sulfide chimneys at the bottom. I have a piece of a sulfide chimney here that I was given by Woods Hole Oceanographic Institution. And these sulfide chimneys are sources of life that we never knew existed on the surface and in the light-bearing layers of the ocean. Light, like as in sunlight. Life is governed by phytoplankton and by photosynthesis. So it stands to reason that life forms developed a way to convert sunlight into energy, and that's what they do. But at these deep ocean vents, there's no sunlight ever. So how come we have a amazing ecosystem of life down there, from giant clams to crabs to shrimp to bacteria to tube worms? Why do we have that down there? Well, we have that because they're relying on chemosynthetic process, chemical synthesis. And when Project Famous from Woods Hole Oceanographic Institution occurred around 1975, the submersible Alvin found the first sulfide chimneys, and these sulfide chimneys turned out to be something that blew away so many people that they started to take a serious look at other moons in our solar system. Yes, they thought about Mars and the potential for underground water on Mars. They looked at Europa, especially because it was an ice moon that showed geysers coming out of cracks in the surface. So that meant there was liquid water underground. And Enceladus on Saturn, same thing. The south pole of Enceladus has these hot spots as seen by Cassini. Just amazing. So because of the finds here on Earth, we've, as Daryl just said, broadened our scope about the possibilities of life. Not life like us, but life in general. And right now, I think finding life in general is probably the most important thing. And then we can work on finding life like us, right?
It's like the saying on the computer screen at the end of 2010, the 2001 Space Oddity sequel. All these worlds of yours except Europa, except no landing there. That opens up ethical questions, I mean, do we have the right to terraform Mars if it turns out there's already life there?
Yeah.
Same for Europa, same for Enceladus and
Yeah.
other places.
You're right, and there will be a big fight about doing just that. Daryl's right. I believe you're right. I will say this though: the Juno probe, circling Jupiter, and doing those beautiful Jovian polar region studies. When that probe's lifetime has ended, they're not just going to let it keep orbiting. They're going to deorbit it and just allow it to burn up in the Jovian atmosphere. And the reason for that is for exactly what you were saying, Daryl, because they don't want to take the chance of polluting a planet or a moon that may have life on it, meaning Europa.
Yeah.
So that's why they're destroying it in the Jovian atmosphere when it's done. Which I think is cool. That's really thoughtful, and that means that the Europa Clipper is not the one that has the lander. The Europa Clipper is the one that's going to scout Europa and look for a landing site. I don't believe it. I think there's the Europa lander mission, which would come next, to actually go to Europa and land on the surface. And they want to find an area where the ice mantle, that thick ice mantle before it gets to the water, is thinnest, or land in the bottom of a deep fissure, and that way you can drill down and maybe hit water. My personal feeling is that they need way more industrial capability than they have to do that very thing. That ice mantle's miles thick, and the moon's only 1,920 miles in diameter.
I watched an interesting video a day or two ago. This is a new vid from NASA about Europa Clipper. They were talking about what people sometimes don't realize, that radiation around Jupiter is so extreme that it would kill a person in pretty short order. And it just like auroras here on Earth, I mean, it's from solar radiation getting caught up in Jupiter's magnetic fields, which are much stronger than Earth's magnetic fields.
Yeah, 20 times.
And then they addressed how to stop that same radiation from destroying the components, computers, and equipment inside the Europa Clipper. And they said, well, we'll build a box of aluminum 1/3 of an inch thick and put all the equipment inside that, and that is enough to stop the radiation. 1/3 of an inch of aluminum.
That's pretty cool. Well, and Jupiter's magnetic field being, like I said, 20 times stronger, as Daryl was relaying, those are particles from the sun trapped in Jupiter's magnetic field, yes. Well, guess what? It happens here too. And so our magnetic field traps the particles and become the Van Allen radiation belts. Okay?
Yeah.
And when people say, how can we go to the moon? We can't go to the moon because we got the Van Allen radiation belts. Well, we're putting astronauts inside of a giant tin can too. And there is some shielding for them. But they don't go out through the very, very thick areas of the Van Allen belts, because it's too thick, and they don't want to risk the exposure to this radiation. So they tend to go out near the poles where the Van Allen radiation belts curve down in. So they can only spend only a few. I don't know how long, but I'm guessing maybe minutes, a few tens of minutes in the Van Allen radiation belts to get out. And then they're winging their way to the moon.
Yes, that's the other part of it. They're moving at such a speed that they don't spend a whole lot of time inside the belts.
Yeah. And at a certain time when they're on their way to the moon, Earth's gravity and the moon's gravity pulling them as they get closer to the moon balance out for a period of time. And at that point, they're officially in lunar gravitational control, effectively, because even though the Earth is still pulling on them, they're closer to the moon, and the moon's gravity becomes bigger and bigger and bigger and affects them more and more and more. And Earth's gravity affects them less and less and less. So there will be a point where that balances. Now that's a point much closer to the moon, but once they're there, they can officially say that they're essentially, quote unquote, free of the Earth's gravitational pull, because should all rockets fail and they stop dead in space, they would be pulled to the moon, not to the Earth. Okay, we're gonna go to 40 on this, then be done. This is really pretty though. Look at this, huh? Look at that. One thing to notice on the elephant's truck is this particular star it looks like this might be the one that's illuminating the dust here. And the dust is scattering some of the star's blue light. And you can see a blue streak right here, which is kind of interesting. It's not the only place. We see those blue streaks elsewhere in this nebula as well. But this is a very dusty, hydrogen-filled region, ionized throughout. It's actually got a lot of young hot stars in here. This is a stellar nursery. But one thing to know is this area here. This dark nebula you're seeing here, this is a very dense part of the dark nebula. Now, what's dense mean? The density of a dark nebula typically is about 30 atoms per cubic centimeter, right? 30 atoms per cubic centimeter. But when you've got a dense cloud, it may go as high as 30,000, right? And if it gravitationally contracts, well, then you can go to the billions and trillions of atoms per cubic centimeter, like we see in air. We've got like 10 to the 20th or so, or more or less, atoms per cubic centimeter, which is the size of a sugar cube. But these deep dark nebulas don't have that much of a density to them. But when they do gravitationally collapse, that's when we get things like hydrogen gas collapsing within there as well, forming stars, dust collapsing, forming an accretion disk around that forming star, and within that you get clumping of some of the dust, and that dust becomes a planet someday. And it may be that the planet is composed of the same materials that we have on Earth, because those are all made in the stellar furnaces. I love this right here. This is beautiful. It's one of the nicest views of it we've seen. Turn off the mask for a minute, the unsharp. Yeah, there we go. Look at that. Okay, one more. Ray wants us to go to IC 1396. Should we do what Ray asks or not?
He wanted to go to the Helix earlier.
Yeah, well, now he wants to go to well, this one's in Cepheus. It's right nearby. But well, the more we wait, the longer we wait, the higher the helix gets in the sky. So that's good. Okay, so this is the Elephant's Trunk Nebula, guys. We took a little tour of it, and it's a beautiful nebula, and it's saved up there now. since we just did another one, I'll save it again. There we go. And we'll go back to our low light mode just for now.
Ray said earlier he'd like to see you image something you've never imaged before.
I think that would be IC 1396. I don't think we've ever done that. See, Ray, here's the thing. This particular camera has never imaged some of the objects up here because this camera was put in before or after, I should say, this particular season came by. So many of the objects that we're seeing are objects that that were never seen before with this. So I think this is kind of cool. We're seeing things for the first time with this new camera, and it's, as we've said many times, this camera is tuned to this particular telescope perfectly. We're right there in the middle of the smallest arc seconds per pixel capability we can have with this camera. So we get the best possible views from this camera with this telescope. It's a matter of the guiding, making sure the guiding is good. If we have a lot of wind, well then our stars may not stack because the images are moving too much. We've had that happen too. Okay, let's now go and search for IC 1396 and see if it's here. Don't know why it wouldn't be.
Small world. We have two cosmics in chat now.
Well, yeah, we have Cosmic Flow and we have Cosmic Ray. What happened? Where'd it go? Wait. No, you don't want IC 1396. That's not what you said. That's the elephant's trunk. Duh. Yeah, sorry. You had mentioned one before, Ray. And I wanted to go there. You asked about it. You asked about another object, Ray, besides 1396, didn't you? If you didn't, we'll just move on. We'll go to the helix. Okay, well... Cosmic Curly. That's funny. While we're up here, I think I want to go... This guy here, what is this guy? Oh yeah, that's what I thought. Good. First time with this camera on the Lion Nebula.
I think Susie has a question for you.
Okay, did you want to say that there are more planets than there are stars? Yeah, there are more planets than there are stars in the universe. That's exactly right. You are right, Susie. That is correct. If that was what you're asking, let's classify this. Okay, H. Hipparchus. Okay, we're going to center this in the view. Alright, and once we center it in the view, that's Hipparchus 110504. Alright, and let's go over here. And oh, there it is. Sorry. Is it this guy? Oh, that's 110154. Was this? Yeah, 110504. All right. So, okay, all right. So from here, let's do this. I think we can do this. No, we can't. We should. Yeah, star. Okay, so that's that star. All right. So that's where we are. And we will, we centered in there, so we're gonna go and that's RW Cephei. Let's see the spectral type. This is a K star, orange star. That's a type 1A, meaning it's a supergiant star. And we will align on that. Okay, that's good. And we have it here in the center, right there. We'll just do this because it came off a little bit. We did it. Okay, there we are. All right, so that's where we are. So now we have an exact alignment. So what I'll do now is go over here and go back to the Lion Nebula, which is pretty cool. Let's check it out. I don't think we've seen this. This is Sharpless 2-132. We've looked at it before, but we haven't seen it with this new camera. It's right nearby. Oh, I see red already. All right, cool. Now let's do this. And yeah, it's close. All right. Okay, that's weird. It's still identifying that star, so we might have a mix-up. Let's do a quick 20-second shot. Cosmic ray, it's actually in quite a number, there we are, quite a number of research papers. Let's do the live stack of this and get out of the low light mode. This is all cleared. This will be the Lion Nebula. Go ahead, sorry.
I don't know about research papers, but seems common sense would say there are more planets than stars. I mean, you look at our little star and it has 9 planets,
Yeah.
if not more, and multiple exoplanets seem to exist around other stellar systems we've imaged.
Yeah.
They seem to be a pretty common thing.
Yeah. Well, when you consider that 75 to 80% of all stars are M-class stars, which are the smallest little percolators, not a single one of them has died since the beginning of the universe. They are the most numerous of all types of stars in the universe, and it also turns out that they have the most planets around them. So it's a simple statistical analysis which shows that there's more planets than there are stars in the universe, because the vast majority of the stars, there are these small little percolators, these small M-class little red ones, okay? Like these red ones you see here, little red one there, little red one there, tiny one there, tiny one there. Those may be little red dwarfs. And those red dwarfs are the ones that have the most planets so far that we have found. There might be more. But it's actually it's actually quite interesting how that has come to be and how it's come to be known. We have another star here that looks suspiciously like a carbon star. Did we find another? Let's go back in here and see. Let's go zoom into that. Back out. Okay. Is that this star? No. Oh, sorry. It's upside down. It's this star.
Yeah.
And this is... Oh, that's the K. I'm sorry. That's the K supergiant. Right there. So this star... Again, stars like this... probably... depending on its mass, it could be destined to be a supernova. Or it could actually end up shrinking eventually and contracting potentially down to a white dwarf. Depends on its mass. But that star is beautiful, and it could have planets circling around its outer periphery, far from the outer edges of the star right now. And they could be getting boiled away slowly because the star is so much bigger. Well, this is a new object for us, Daryl. We haven't really seen this one with this camera at all.
Not that I recall.
It's the Lion Nebula. I don't see a lion, but then again, I wasn't expecting to.
I see lines of stars in this image.
Are you talking about like here?
Closer to the nebula, to the lower left.
There's one there.
There's 2 or 3 right there.
Like right here? Oh, yeah, there's some right there. Like that one?
Over back on the right.
Alright.
The bright star to the right. I see a short line and a long line.
You here?
Just to the right of that.
Oh, you got this line.
Yeah.
Yep.
And others, and I see them down below, and all over the place.
Yeah, look at this, guys. As Daryl was saying, look at this line of stars right here. Now, Daryl said something which might be true, I think. It's like, what are the chances that stars would just have a chance alignment making such a straight line across so much space, several light years? The answer is that it's possible that could be a chance alignment because there's so many stars, but in this particular location there's not really a whole lot of stars. So is it possible maybe that, and I'll point out the chain that I was talking about, is it possible that this chain of stars, say right here, is random? Or is it possible that this chain of stars that was formed here was created by some type of shockwave at some point? Don't know. That would be a really good thing to research. I think I see where the lion, I think this is the lion's mouth. Lower jaw here. Open mouth. Roar. Either eyes or a nose. Or this is the nose and there's the eyes. Lion's mane. Oh, actually, it stands out like a sore thumb now. Looks like a lion's mane right here. And this looks like the lion's face. With his mouth. Wow. If that's what it means, I'm not sure. But I can see why somebody would name it the Lion Nebula.
Interesting gray band across the lower right section of the nebula.
Oh, right there, yeah.
Yeah, I don't know if that's reflection nebulosity or what. more gray up to the upper left of that.
Yeah, like up in here, right?
That.
Yeah, this could be possibly just illuminated dust by the stars in the area, because you do get that too. You know, not all dust is gonna scatter the blue light of the stars. Some of it will just reflect. Its light will be reflected by the dust. Depends probably on the nature of the dust. It's all about the same size. There's only a few microns across, or even smaller than a micron, which is tiny. And so that is possibly what's happening here. Or the density isn't high enough to actually see blue, but it might be just enough to see the reflected or scattered light, and it shows as gray as Daryl was talking about, and not the actual blue that a more dense nebula would show, like we see in the Pleiades, which, by the way, are probably up by now. Well, they're up here in Connecticut. I'm in Connecticut. The telescope's in Arizona, and it's midnight here, so it's clearly the Pleiades is up here. We're seeing more detail. Let's add the unsharp mask back.
Cosmic flow. It may be a little early for Arizona to see the Pleiades yet.
Yeah, let's go and bring this up. Let's zoom out of this a little bit. Okay. Okay, we're only getting Cassiopeia here. Andromeda, Triangulum. Here's
You know a place
Perseus.
we never look at?
What place?
Lacerta.
Yeah, you're right.
It's above Cepheus there.
Yeah. Is there anything good in Lacerta?
I want to say there's some. Let me find out. Hang on.
You got Milky Way in there.
Yes.
We got a Vandenberg object there. We have the Cocoon, which is not quite in there.
Lacerta is lizard.
We can show that right here. Here's the lizard. It's a very small constellation.
Yeah. I don't know if it's worth looking at or not. There's
You
let me
have
see.
Vandenberg 151. It's a little reflection nebula in there. The Wizard is just outside of it.
It's always cool.
Yeah.
Anyway, proceed.
Okay. But you're right. We don't look at it.
No, well, it's right up in that same neighborhood as Cepheus and
No, we're literally on the border right now.
Cassiopeia.
You see this though? We're on the border of it. We're literally right on the border. Here's what we're imaging. Okay, and the border's right here.
I ran a quick search.
Mm-hmm.
There's like 21 deep sky objects in Lacerta, but none of them rang a bell with me. How good they'd be.
Okay.
Again, let me look for something else.
Yeah, Kathy, that was Twinkle Twinkle Little Star. A different version of it, yeah. I thought it was cute.
The Pleiades and the Hyades are up here in Colorado, but let me take off an hour. So,
Well, that's what I was trying to do before.
Pleiades might be above the horizon, but they'd be very low right now in Arizona.
Yeah, this is set up for Arizona right now. And it's right. Is this it right here? I think this is it. Oh, no, that's not it either. Wait, that's Electra. Yeah. Here's a Pleiades. They're way, way down. Way below. See where they are on the horizon? They're right. They have just risen.
Yeah.
So we won't be able to see that. Well, look, we got later in the season, guys. It'll be here before you know it. But hey, the Triangulum Galaxy is available to us now.
Sure.
We should probably check that out with this camera. All right. So we're going to go back here. We have 35 images. This is the Lion Nebula, guys. And some of you said you saw the lion. That's cool. Those are all fanciful names, of course. And there's a beautiful K supergiant right next to it, which is so cool. It looks like it's roaring at it. Okay. We'll do 37 coming in moments. No rejections. And when we say 37, what are we doing? We're taking 37 images and stacking them after aligning them with each other on top of each other. When we do that, we get rid of all the noise in the image that's created by digital cameras. Very cool. And thus we have, and thus we have a beautiful, image that doesn't have a lot of noise in some of the fainter details. If we're taking dark nebulae especially, we want to avoid that. All right, so while we're here, all right, in this region of the sky, and I'm going to get out of this. This is going to be up on as a Lion Nebula. It's going to be up on our server if it's not already there. Okay. Oh, do we have a blue nebula in there?
Right in the very bottom right corner.
Yeah, let's see. Let's go back to the live stack because it'll still be there.
I saw that.
All right, so let's go up here. Oh, look at that. This is the rest of that nebula that we took with the other camera. Check that out. Oh, man. That's really pretty. We did do this, remember? It had a beautiful red component and a blue component. Oh, wow. Yeah, let's just go back out. And let's fit the width.
Some interesting dark lines in that blue nebulosity,
Yeah.
which I assume is dust.
Right in here.
There's one, there's a very sharp one to the left of what you pointed at.
Oh, right here?
That right there.
Yeah.
And the big one, there's another sharp one to the right, upper right.
We got one all
Right
in here.
there.
See that?
And that. But I meant specifically in the blue.
Okay. I seem to remember with the other camera we could see this whole nebula in one view, but that's because the other camera had a 4 full moon by 3 full moon tall field. This one is a 3 full moon by 2 full moon tall field, because the different camera had us. We actually have a smaller field of view with more pixels, so we can see more detail per square inch, basically, okay, or per square pixel, than we could before. More arc seconds per square pixel. Part of me wonders if I should just drop down to the lower right and just take the rest of this guy.
sure.
Yeah, that's actually cool. We might as well finish that out. That's a good idea. Okay. So we're going to come out of here and we're going to leave Lion Nebula up because we're going to do some shots of that. So we're going to bring up the Lion Nebula down below. This is in the blue. So what we're going to do is move a little to the right. In other words, west. Center that up. There we go. Okay. You can even see the blue in here now. Look at that. That's really pretty. We can see the blue. Okay, and then we're going to go south, young man. As opposed to go west, young man.
Who said that?
Go west, young man?
Yeah.
I don't remember, actually. I'm sorry to say.
Horace Greeley said it.
Ah. This is a really big blue nebula. Look at how big this is. I didn't know that. Okay, 25 seconds.
That's why there's a town named Greeley in Colorado.
Oh, well, that's why you know that. Cool.
Yeah.
All right, let's go see that. This is going to look beautiful when it comes in. It's the other half of this nebula. Okay, so there's the top half. And we'll clear now and get the bottom half.
Maybe call this Lion Nebula 2. Unless it has a name.
I think it's all part of the Lion Nebula. See, there's the upper part. Look at that.
Oh, okay.
Look at that. Wow. Let's do alignment of the colors. That's pretty good.
So is that oxygen or reflection nebulosity?
Well, that's the question. I think last time we did this, and you're right to ask that question, I think, because last time we did this, we questioned whether this was a reflection nebula or whether it was ionized oxygen, which can look similar. But I thought that maybe it was a reflection nebula. However, I've seen other shots that show it a distinctly more greenish tinge, like it was oxygen. So I don't know at this point. Have to figure that out. I'm sure you could look that up. Probably you probably have the answer in 2 seconds.
I would guess not. Reflection nebulosity. What bright star would be illuminating it? But then again, I mean, what's making the oxygen?
Yeah, exactly. Well, remember, there's dark nebula here, so there might be a star buried in behind all these molecular clouds that is able to do that. Could excite this hydrogen, but I don't know. Maybe it's some of these stars right here, or these stars right here, or these right here that are causing this to glow. I'm going to guess in this region. But then down here, these same stars, ultraviolet energy, could be causing any oxygen to ionize down here. It depends on how far that is in space away. It also depends on many other things, like these stars too could be having their blue light scattered down here. Yes, the space is a dirty, filthy place. It's got all dust balls everywhere. Hey, bro, what's up? Hey, Marco. Yeah, that's nice. Let's get that down out of the way. And let's actually get rid of this for a minute. So we can actually bring this full screen, more full screen, to watch it developing. Yeah. Very nice. Look at how this hydrogen gas right here is overpowered by this particular part of this blue nebula. That could be density driven. Not sure. As the winter... Oh, go ahead.
I would wonder if the bright blue star,
Oh, yeah.
just above the blue nebulosity, might be the source of the energy.
Yeah, this is... It's buried in it, isn't it? It's got that cloudiness. It might be buried in it. This is an interesting bar here with this dark nebula here. We drop it down, see a little more of it. Wow.
Might make a pretty picture if you wanted to do a mosaic of it.
Yeah. We would have to, just to get the top half in here.
Yeah.
It just goes off the field of view a little bit.
I mean, the top left corner of the blue was just barely showing at the bottom right corner of the first image.
Yeah, so it'd be a...
Excuse
Oh,
me.
geez, bless you.
Snuck up.
Yeah. It'll be a diagonal mosaic, but that'll work. That's why I left lion in here, because it's all part of the same. This is a beautiful contrast, though, in the types of processes going on in the universe. Alright, we'll let this go a few more. So we look at this. This is actually it's beautiful. This beautiful area here. This has got a lot of detail in it. So hopefully we can be able to pick that up. Looking at some of the versions of this online, it shows that this may be reflection nebula. At least it shows us that blue color we expect to see in a reflection nebula. And this is an arc which comes out and continues up, starts to curl around a little. And you guys will notice that the sheer number of stars here kind of overwhelms the nebula, doesn't it? That's kind of what we see a lot.
Still in Cepheus?
I think we are. Let me.
We're very close to it. Milky Way, lots of stars, lots of dust.
And we are in Cepheus. We're in Cepheus right here. And we're right there. Let's go looking. Yeah, it looks like we're still in Cepheus because there's the border.
Yeah.
It's almost like we're half in, half out. we're partially in Lacerda. Okay, we're gonna redock our stacking dialogue here. And let's bring the telescope back. Okay. All right. So we're gonna go to 21 here. And we'll save it under Lion. Okay, let's go now to a new object. Oh, look at these guys. That's why the lion was roaring. Somebody stabbed it with a knife. All right.
What's that?
I'll show you when this comes up. Oh, there was a line of stars here. And it looked like it was stabbing the lion. All right, let's see here. Now.
Did you give it another name?
No, it's all part of the Lion Nebula. So they'll all be there. We can mosaic them.
All right.
And let's now see. I was thinking from here we should. Oh, stop. I was trying to get over to M33. And then we can try. We can try looking at, hopefully it's up here anyway. So let's see its altitude. Altitude 44. I think this is just visible to us.
About as high as Polaris.
Yeah. But looking over the northeast side, it's got the roof. So I'm trying to see. I think 44 allows me to see over the roof. And I think it's right here. Put it right here. I think I can see it just by doing a quick 10-second shot. Not even stack it, just do 10,000 milliseconds. Quick enough. Let's see what we got. Oh, it's up there. Okay. Oh, that was totally wrong. Okay. Well, that's good. At least it's right nearby.
Mark, excuse me a moment, please.
Sure thing, Daryl.
Right back.
Okay. So what we're gonna do now is bring this down. We're gonna bring it down by actually raising the telescope up north. here comes Measure 33. Beautiful spiral galaxy. It's actually a very messy spiral galaxy. It has loosely spiral arms. They're actually kind of loose. And we classify galaxies as SA, SB, SC. That's the classical classification. It's changed a little bit because we've noticed that there's many more barred spiral galaxies. Barred spiral means that the nucleus is extended before you have the spiral arms come off. That's kind of what we see in our own galaxy, oddly enough. Okay, let's zoom in and make sure that our focus is still good. Yep, looks good. That's NGC 604, as you'll see in a minute. It's a large star cloud, a nebula, stellar nursery, massive in there. Okay, let's now, this will be a 25-second shot. MJ Zachariah, how are you? Yeah, this is M33. We'll do Measure 31 on our next trip. It's not far away, but I do want to get to the Helix Nebula, which is on the other side of the sky. Okay, we're going to live stack this, and it's 12:30 in the morning here, so we have to think about getting ready to close up. And I want to make the last object something that everybody can see pretty quick, and that will be, well, M31 can, but that'll be, I think, the Helix Nebula. Okay. I may have to change I do, okay. Bring up my threshold on this guy. Let's hope that works. If it doesn't, raise it a little more. No, but this is how much oblateness to our stars we would tolerate. The answer is not much. Okay, there is the galaxy. You can see that. Look at that shape. There's only one frame captured right now. Namrats, how you doing? Okay. Okay, we got two now. Looks pretty. All right, let's go back here. There's NGC 604, that star nursery, that stellar nursery. All right, so let's go to our histogram. Set the colors. Good. Now let's see where it wants to go with processing. It's going to do that. Yeah. I don't like that. So I'm going to move this curve up the white curve. The white is the average of our red, green, and blue. And we're doing that to darken the background, especially without losing any data. And as long as we don't cross over that curve and start going down the curve, we won't lose any data. See if I do that. Watch. Hello, Daryl. Welcome back.
Thanks.
So if I do that, you'll see that we lose data. So we go literally just shy of the top of the curve, and that gives us the best. And while we have only a few images, we've only taken 4, we'll take this midline and we'll drop it down, and that'll soften the noise that we see in here. There's 604. This is a nebula in there. And we also see some supernovae, like right here. This is a supernova. Now you can tell because it has that typical greenish blue look of the filamentary structure of supernova we see in our own galaxy. Whoops, sorry. And down here,
One over at 3 o'clock.
yeah, you're right. I gotta grab that one too. You're right. There's one right here. And as Daryl said, one over at 3 o'clock right here. Yep. So we can see them in here, and it's a, like I said, it's a messy looking galaxy, I grant you. But what's nice is we can see all of it. And that's what we look at. That's what we see. It's a really pretty galaxy. Very pretty, wow.
When you see the galaxy down at 6 o'clock from the nucleus, looks like there's sort of a suburb out there.
Where?
Down
right here?
right there.
Yeah. This may be one of those OB associations, which are hot O and B stars. Remember our nomenclature, O, B, A, F, G, K, M, where O's are the hottest and bluest, and M's are the coolest and reddest, and the O's and the B's are the hottest stars in the universe. So they tend to be very, very strongly blue. The spiral arms is where they form, so those tend to be very strongly blue. The core is usually older stars, and those stars are not quite as blue as elsewhere. And I'm gonna just try to pump this up a little bit there, so now you can see more detail there. That's beautiful. Let's go back to our histogram and darken up the background just that little bit more. Here we go. Let's color correct it one more time. As each frame comes in, we should be color correcting it. See, like that. So we see the blue color, and then we see the yellowish color in the middle. That's really something.
M33 and Triangulum is another member of our local group of galaxies. It's a little farther away than Andromeda Galaxy is, M31. I think there's some talk whether M33 has gravitationally interacted with M31. Wouldn't surprise me a bit.
Yeah, we've talked about that before as a possibility. M33 looks like it's been torn apart a little bit, and Messier 31 is a lot bigger than Messier 33, and it's a lot bigger than the Milky Way. You know, the Andromeda Galaxy is Messier 31. And next time we open up, we're gonna view the Andromeda Galaxy as well. And here, in this galaxy, let's zoom in now that we've got 15 shots stacked. In a shot like this, we can identify the globular clusters in this galaxy. Some of these tiny little dots you see here are actually clusters of either hundreds of thousands of stars or more in this galaxy. They're the exploding snowballs of stars, like Messier 13, the great star cluster in Hercules, like Messier 22, the one just above the teapot in Sagittarius.
Exploding?
It looked like an exploding snowball of stars. Yeah, like it's just like, it looks like an explosion. Poof. But they're just a gravitationally bound spherical collection of stars. Not exploding in the true sense of the word, of course. Look at, if you're out here in the suburbs on a planet formed out here, you'd have the whole galaxy to be looking at. You'd have a really strange looking Milky Way. In our galaxy, let's say this is our galaxy. Now this isn't exactly the same type. Ours is a barred spiral, not a regular spiral like this. We're just about 2/3 of the way out. So in this example, let's say we were here. We look toward the center of our galaxy. We see the center like we do now in the summer sky. Then you look to the left. As we look to the left, we start to see Cygnus Milky Way in our galaxy. As we continue looking, we see maybe this arm of the galaxy out there and see yet more Milky Way out there. But from here, they would only have Milky Way in one direction ever. They wouldn't have any Milky Way in this direction, which is kind of interesting. All right. "20 shots. Look at that. This will make a very pretty shot.
Yeah.
Here's the nucleus of the galaxy. A lot going on in there. Okay, we'll save it here. Not yet, I won't. I'm gonna name it Measure 33 Triangulum Galaxy.
Why is it called Triangulum?
Because it's in the constellation of Triangulum?
Well, I mean, what is Triangulum?
Oh, is that the drafting triangle?
I believe. That or Carpenter's Triangle.
Yeah, we can go look. Alright, so we're in Triangulum right now. There it is. And if we were to show the artwork, it looks like we're seeing the triangle. Why would they ever do that? I just don't get it. Kind of nutty.
Well, they probably had 3 stars they needed to do something with. A lot of such constellations are in the southern hemisphere where they're like man-made objects.
Yeah, like the Fornax,
Yep.
Microscopium.
Telescope, yeah. Sextants, the sextant.
Yeah. Robotium, the robot. No, I'm just kidding. There's no robot. Namrat says, Omega Centauri. I would love to show you Omega Centauri, but we can't see it now. And in this observatory, the wall prevents us from seeing it. I've tried. If we were going to stay in this observatory, I would have actually put the lifting column on this telescope, which is basically a hydraulic pier that goes up like a linear actuator and doesn't lose any accuracy as it does. It's a very, very highly precision piece of equipment from Progressive Automations. And that would have been able to lift twice the weight of this telescope and lift it up above the wall for some of the viewing of these objects. Problem with that is you then expose the telescope to the wind. and inside a building it's a little bit shielded. But you'll notice we are getting some wind, because we see that we had, okay, and let me just kind of bring this back. All right, we actually had some, bring these down. Oh wait, that's the wrong thing. I was in the wrong one, sorry. Okay, see how we had some failures? That means that there's a little bit of wind that came in to kind of bump the telescope just enough that it could make our star images a little bit out of round. And we don't want that. So let's see if we have lost the wind. No, we have not. Let me see if I can save it here and then save it again. So we have 27 shots taken so far, not counting those 3. So we've been exposing this galaxy for a total time of 11 minutes 15 seconds. All right. Yeah, and this just, we're getting some wind down. It's making the telescope bounce just enough that it is not comfortable adding it to the stack. So that might just, I mean, that's okay. 27 images, that's not bad. So I think we've saved on that, yeah. I think I saved exactly a scene. So that might be red as well. No. Okay. That'll make a beautiful photo. And so we will make this photo is now available to you. If you're a member of the Patreon, which we have, please join our Patreon. Love to have you. At a rather modest tier, you can get the highly processed photos of everything we take, which are just beautiful. You can get them, you can put them yourself on some products, or you can go buy products with them on them. It's up to you. So let's now go back to our low light mode. And I think it's time for us to go to the helix. So we're going to go and try and locate the helix. It's all the way on the other side of the sky. We can do it. It's a helix galaxy. Did you see that?
You see that?
Okay. Let's go to the helix. You watch the telescope come right toward us now. It's going to head out the front end of the building right now. Here it goes.
Under Aquarius, not far from Omaha.
Yeah. Let's get to it.
Ray, Mark, I'm sure will check me if I'm wrong, but I think actually the new place they're looking at is also in Benson, Arizona.
Yes, you're correct.
So yes, Benson, different place though.
It's actually 10 minutes, if that, from the current location. Let's see if it recognizes anything in this region. No deep sky objects, so let's do a 10-second shot. I don't see it yet. It may not be in the field of view yet because we went all the way across the sky. don't see it in the view. That doesn't mean much because it could be right nearby. So let's go to Fomalhaut and align on Fomalhaut, and then we'll be good. Well, there it goes. I don't think that's Fomalhaut. Fomalhaut's a lot brighter.
Lonely in the south.
Is that what that means?
No, that's what I always say.
Oh.
It's all, Fomalhaut is a bright star down low in the southern sky in the fall, and it's all by itself, and I always call it lonely in the south. It's the only bright star in the area. Actually, if you know how to find Saturn right now, which is in eastern Aquarius, if you go straight south and then jog over just a little bit to the west of from Saturn, you'll see Fomalhaut, bright star all by itself. Constellation Pisces Australis, or Austrinus, southern fish. And I've heard some debate about how to pronounce Fomalhaut.
I say Fomalhaut. May
I've
not be
heard it-
right.
I've heard it said Fomalo.
Hmm.
I think that might be a French pronunciation. I saw a debate on that somewhere recently. Might even have been here. Fantasy might have corrected us, I forget.
Mm-hmm. $22.57. No, $22.52. And minus 29.
I think maybe that's Fomalhaut right there.
Yeah, that's better.
Yep, Fomalhaut.
Yeah. Alright, so we're going to do that. And we'll center it in the view. And then we'll make our way up to the helix. I didn't want to go hunting around. And I figured I would actually get this aligned right. I'll be out there in a couple weeks. And I'm going to work on the alignment, I think. And I'm going to work on doing some more dark frames. I have a 60-second dark frame ready to go on it already that Marianne did. Okay, so that's set. So it's a plate solve. And it's 2257. And if I say sync right now, oh, that wasn't good. That wasn't right. Yeah, see, I screwed it up. I was connected to the wrong thing. So I'll just have to do it this way again. I was trying something. This will be quick. Alright, so we'll say plate solve and resync. Alright, we'll do it the other way then. Alright. this. Oh, I had the wrong coordinates. I had these coordinates in there. I'm sorry. Okay, I screwed that up. Alright. Yep. That wasn't the right thing to do. And it's really this and this. I'm actually inputting coordinates up here right now. I'll say sync. Alright, there we go. Now we'll do this and Fomalhaut will come back like we did just there. Excellent. Okay. So now we can go back and do this again. Sorry about that little snafu. Now we'll go here and it should be almost in the middle. There it is.
Lubo and JSCO, hello.
Hey.
They were saying late on the 5th, Zulu time, Greenwich time. So it should have hit earlier today. It could always be late though. Last I saw though, no, they hadn't reported any auroras starting yet.
Interesting, because the auroras were not showing up on the telescope view of the poles that you get with these solar observation programs.
KP is currently 1.67 still.
Yeah.
Quiet.
Very ultra quiet.
And the auroral oval is dim and small.
Yeah.
Well up north of the U.S.
Yeah.
So.
Okay. Okay, we're gonna do on this guy. I'm gonna try a 45-second shot. Now we're guiding on this. We should be okay. And we're gonna go into our deep sky mode now. The last object will be here that we did. Right, Mission 33. That's been saved. That's up on our server now. If you want to go check it out. Interesting little jog in this part of the galaxy there. Well, that'll be visible. We didn't get any satellite trails through it. We're luckily off that a little bit. JSCO, how you doing? Daisy and Zoe, how are you guys? Lubo, how are you doing? There we go.
Lubo, they said when the X9 flare happened that they didn't see much of a coronal mass ejection accompanying it. I was a bit surprised when they said that there was going to be a geomagnetic storm hitting Earth from the X9 after all. I know it was a huge flare, but it wasn't much of a CME from it. They said the X9 flare was the most powerful one yet in this solar cycle.
Huh. I don't... X9... I mean, X-class flares are stronger than M-class and so forth, but X9 is not an X42 or something higher, so... I don't think X9 is the most powerful. Haven't we had... I mean, just the other day, not the other day, just a couple months ago, we had auroras here. We had auroras visible at the observatory here in Arizona.
Yeah.
That was a far higher X-class flare. It was actually on the border of a Carrington event. It was actually kind of along the same lines.
I think it still had a ways to go to be a Carrington event.
Well, yeah, but
Well, I remember what you mentioned. There was another strong X-class flare
yeah.
not long ago, and they said this one was stronger.
As an X9, huh?
9.1, I believe.
Okay. I just want to point out something here. Guys, here is the Helix Nebula. It's a planetary nebula. This is a nebula that results from a star running out of hydrogen, swells into a red giant, okay, and eventually will shrink back down once all the nuclear capability ceases. But as it swells into a red giant, it will spew off its outer layers, and that's what we're seeing here. The red, you know now, is hydrogen, and this bluish mass in here, this is oxygen. So we see the hydrogen and the oxygen that the star was made with being spewed off here. And in the center is a star which, if you notice, it's blue. That blue color is a dead giveaway that this star is very hot. And this very hot star is known as a white dwarf. It's the remaining non-fusing core of the original star. Alright, so there's no fusion going on anymore. This is just a hot remnant. And it's made mostly of carbon and oxygen atoms. Compressed together. Not even atoms, nuclei. Compressed on this white dwarf, the size of the Earth. And if you took a sugar cube full of this and you could bring it to Earth and put it down and weigh it, you'd find that a sugar cube of this white dwarf would weigh about 2,000 pounds, about as much as a small car. So that's what a sugar cube of this compressed stuff would weigh. That's quite heavy. Now the next step up is the neutron star. And the neutron star is an even more compressed stellar remnant in the core. This is a white dwarf, not a neutron star. You need a much more massive star to make a neutron star. But if you had a neutron star, a sugar cube of that material, if you could manage to weigh it here on the Earth, which you couldn't, but if you could, it'd be 426 million tons. A sugar cube. That almost seems stupendous, but that's exactly the type of thing that the universe tosses at us.
And what's really scary, that teaspoon of neutron star, well, if you separated it from the gravitational field of the neutron star, it would dissociate violently, to say the least.
Yeah, your spoon wouldn't survive, or would you, or the ship, or
the planet.
Yeah, right, exactly. Or some planet nearby you're doing it on, yeah. So, not a good idea. Do not take that material. But, it is kind of interesting to talk about it because of the analogy. And as we talked about, okay, this right here, this is the white dwarf right here in the middle. Okay. You'll also notice, in looking at this, there's some arcs of material out here that are really interesting. There's actually another arc of material here, kind of hard to see, and there's some really good detail inside this inner area. Pretty cool. Let's zoom in. Now we've got 7 that we have captured already, and 1 has been rejected. Let's see where that rejection was. Right in the middle. Okay. Yeah, they were all pretty much in the 7s except for one outlier here. This is the outlier. Yes, thank you, Daryl. Yes, if you guys please do hit the like button. And of course, we'd love to have you be a member and help us out with our Patreon. It's not making me any money because I'm not taking any money for this. But if you could consider it, that'd be wonderful. Because this helps us very greatly. Okay, you'll notice that when you zoomed in like this, you can see that blue color pretty easily here of the white dwarf. Now this nebula something like 600 light years away, so you're seeing as it was 600 years ago. So it's the closest planetary nebula to us, and it has this white dwarf in the center that's the size of the Earth. It's 600 light years away, right? This is a very tiny object to be seen like this, so it has to be very bright to cause this big bloating image on our sensor. Okay, and just as a matter of reference, Alpha Centauri is made up of 3 stars, right? You have an A and a B component, and you have a C component. Well, let's take the A component. It's a star kind of like the Sun, and it has a diameter. Now, the Sun's diameter is 864,000 miles, right? Well, if you had a quarter, a quarter, how far away would you have to move it from you so that the diameter of the quarter that you see in your very powerful telescope was the same diameter of the actual star in the sky? You'd have to move that quarter 724 miles away for it to be the same size as Alpha Centauri is in the sky. So you can see that's for a big star, or a massive star that would dwarf a white dwarf. And the white dwarf being 600 light years away when Alpha Centauri is only 4 light years away, you can see that that white dwarf has to be incredibly, colossally bright to be seen from that distance at that size. Okay, I can turn off the unsharp mask. The noise is a product of the number of exposures. We do not have enough yet. You can see though that there's a high bench. We can also bring this back. I was on the... This will help. You can see some of those radial spokes that we see in the helix. Hey, random. SMA Sky, how you doing? Nice to see you. Okay, let's yeah, there's noise in here, right? Well, one of our other things is this, the all sky cam. Ah, well, there you go. Now you see why there's noise. We have some clouds. Yep, there's some clouds. Actually, they're covering the whole sky. How about that? So here's our constellation overlay. Right here. So you can see some of the constellations. All right, and it did look like there was some problems with noise, and so we're not getting a very good representation of this. So here's what we're gonna do. We're not gonna save the helix. We're gonna dump it, because we'll come back to this another night when we actually have a good quality night. It started off good, but then we got some high clouds to come in, which kind of stunk. But I will say this. I hope you guys had a good time. We're going to end it for tonight because obviously we have some high clouds. This is the all sky cam that I actually built, and this software is a software that's publicly available, called Thomas Jacquin's all sky camera. But in our view here, the clouds are getting worse too. In our view here, this is Phoenix, Arizona, which is like 80 miles to the center away. And when we see high altitude clouds, you'll see them as kind of like this, because they're so high altitude they actually pick up the lights of distant cities. But when they're the puffy cumulus clouds, starting about here, the clouds are black going across the sky because they're lower altitude, so they don't get the light on the bottom of them. They get the light here to about here, then it gets blacker and blacker until it's all black out here. But the high altitude clouds, they're very high altitude and they can get the light from anywhere, so they'll show up, and that kind of ruins our night. But there you go. So, actually, yeah. One last thing. We won't be able to see the helix tonight, unfortunately. But I wanted to show you, every night we make a time lapse. So this is a time lapse from yesterday evening. Okay, this is the morning, sunrise. Okay, I'm skipping ahead. Okay, and as it moves across, that's a lens flare. Here's some clouds, you see them there. Then as it moves across the sky, after the sun sets, the camera flips into night mode, and you'll see an initial over brightness like that, and then it goes away, and there's our Milky Way for the evening coming in. You'll see satellites and meteors. Okay, we saw several satellites. There's a meteor right there. I see that all my data has gone, so I have to add that back in. Oh, that was interesting. That was probably a plane. It looked like one. But we actually caught a re-entering, there it goes, a re-entering spacecraft one night. Okay, let's go back just to confirm. Here it comes. Yeah, you can tell it's a plane. If you notice, you can see there's like these distinct little flashes. This is a 15-second exposure, and if you count these flashes, you'll see that they are the number of flashes that correspond to the FAA mandated flashing rate in 15 seconds. So, but that's cool. Anyway, that's what we do on a nightly basis. Here's the data that was supposed to be there. Alright, so we come back to this now. So it tells you right now that we have 11 p.m. going on 11:30, 11:45. And look where the Milky Way is already. Okay, north, south, east, and west, because we're looking up into the sky. The Milky Way is already over here, all the way out into the west, setting. But the winter Milky Way is what's coming up, which is kind of cool. And there's the Pleiades right there. You can see the Pleiades right there. Right? And that looks pretty. And here's the Hyades with Aldebaran. And
Jupiter up above the Hyades.
there you go. That's right.
Right there.
And we have Orion right here. Betelgeuse, Bellatrix, Rigel, Safe, Alnilam, Alnatak, and Mintaka, the 3 belt stars. And then we have the Sword of Orion down here where the Orion Nebula is. So this is Taurus, the bull. This is Orion, the hunter. These are the Gemini twins coming in over here.
That's Mars.
That's
below.
Mars below. Where's Mars? This?
Yes.
Yeah, because that's a little. You can see it's a little orange.
He was under Castor there on the 2 stars above at the top left.
Right here.
Pollux on the left, Castor on the right. He was under Castor, but you might remember Mars was in conjunction with Jupiter there in the horns of Taurus a while back.
Mm-hmm.
And Jupiter is still there. He has moved a little bit, and Mars has moved all the way over into under Pollux now in Gemini.
Okay.
And he'll continue moving on over into Cancer.
Mm-hmm. Here's Sirius, the dog star.
Isabella's here.
Hey, Izabela, how are you? Nice to see you. It's early morning for you. So yeah, so here is Orion, and that's coming up. So this is going to be our playground here in just a couple months, right? But you'll notice that we can see the Pleiades very nicely. We can even zoom in and see the nebula around them, which is really cool. And you'll see it get brighter and brighter. But just before dawn, Orion is down here at that southern horizon. Here comes dawn. And satellites. That's pretty cool. Very nice, very nice. We also do star trails. Okay, here are our star trails. And let's go to the other night and see if we can see them. So, if there's clouds, you see clouds too. Okay. And we see clouds because there were some during the middle of the night. But the star trails are pretty. Oh, look at this. Plane came through. And this is really an easy way to see planes and satellites, because they show up like this on the on the star trails, because they're oddballs. They don't follow the round curvature like the star trails do. So pretty neat. So there you go. So right now, as you notice in our live view, we have clouds that have now covered in. So we're going to say goodnight for tonight. And I hope you guys had a good time. It was very nice to see you guys here. PG is here as well. Hi, PG. That's Petita. I just noticed that you said hi. JSCO. We see satellites at dawn and dusk quite a lot because of the fact that at the lower altitudes, the sun can illuminate them just at sunset and just before sunrise. So they see the sun bright and bright, but here on the ground it's still dark at that time. So they will be illuminated, and they tend to be brighter because they're lower altitude, and we see them a little brighter. They also move faster than the higher altitude satellites by far.
Good night, Mark.
Yeah. All right, everybody.
Good night, everybody.
You have a good night, and we will see you on the other side. Good night, everyone.
Good night.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the view.